Hello guys, welcome back. Chapter 14, Day 2, Introduction to the One Sample T-Test. Alright, so what I'm going to do today, I'm going to do this as efficiently as I can, as I'm going to show you the one sample t-test. Now a lot of this is going to look very similar to the process for the one proportion z-test. There's a couple changes here and there. I'm going to make note of those changes, but generally speaking, the process is identical to the one proportion z-test. So let me take you through the one sample t-test. A pharmaceutical company has developed a new drug to reduce cholesterol. A regulatory agency will recommend the new drug for use if there is convincing evidence that the mean reduction in cholesterol level after 1 month of use is more than 20 milligrams per deciliter. All right, I'm going to underline something right here, and I'm going to explain why in just a second. The mean reduction in cholesterol level after 1 month of use. Okay, because a mean reduction of this magnitude would be greater than the mean reduction for the current most widely used drug. A pharmaceutical company collected data by giving a new drug to a random sample of 50 people from the population of people having high cholesterol. The reduction of cholesterol level after 1 month of use was recorded for each individual. The resulting sample mean reduction and standard deviation of 24 and 15 respectively. All right. So the first thing we do with any test, whether it's a one proportion z-test or a one sample t-test, is we identify our parameter of interest. Now, with the one proportion z-test, we would say p equals, because it represented the true proportion. That's where the p means. It's the true proportion. But now, since we're talking about means, we're going to identify the parameter as mu. All right, so our parameter is the true mean reduction in cholesterol level after 1 month with the new drug. All right. The one thing, when I looked at a lot of your guys' responses, you want to be very specific in your parameter of interest. Okay, it's not just saying that the true proportion, or the true mean. You got to be specific in your identification of the parameter. Okay, this course is all about context, so you got to be able to write these things in context. So that's the parameter, the true mean reduction in cholesterol level after 1 month with the new drug. Now, just like with the one proportion z-test, we're going to have a null and alternative hypothesis. And just like with the one proportion z-test, our null is going to be that mu is equal to some value that is given to us in the question. And so in this question, the key is 20. So right now, the current drug has an average reduction of 20. So in order for the new drug to basically get approval, it has to show that it's better than 20. So the null hypothesis will be 20 milligrams per deciliter. And we want to show that the new drug has a reduction that is significantly more than 20 milligrams per deciliter. All right, so just like with the one proportion z-test, the alternative can be greater than, the alternative can be less than, or it could be not equal to, just like it was before. And if it is this, remember, if you do a not equals to, what we want to do is we want to take the p-value and multiply it by 2 when we get to the end. So that's the only kind of catch with this not equals to. So this one, we're just strictly going to do a greater than test. Okay? Now, check the assumptions and conditions. This is going to be the exact same thing we saw yesterday. All we're really looking for is randomization and independence. So what do we have here? we have a random sample of 50 people from a population of people with high cholesterol. Okay, so we have a random sample of 50 people. Sample of 50 people. Okay. And therefore we are going to assume the reduction of I don't know how to spell this. Cholesterol level is independent for each person. Okay? So those are the exact same things we just checked yesterday. The test name is called a one-sample t-test. Now, I'm going to get into this whole t thing in just a second. All right, this is something that if we were in class, I would spend much more time talking about it, so I'm just going to keep it as simple as I can. So the test statistic in the one proportion z-test, was the z-score. And we found the z-score by doing p hat minus p over the square root of p times q over n. All right. Now, in this test, it's going to be a t-score. And I'm going to explain why it's t in just a second, but just follow along with me here. So we're going to do x bar minus mu over s over the square root of n. All right. Now that s is the standard deviation of the sample, because we don't have the standard deviation for the entire population. But this whole thing should look similar to what you did yesterday in the notes and then in the 2 homework questions. So our sample mean was 24. Okay. 24 minus what was expected, basically our mu of x bar, our expected was 20. So we can see right there that we are 4 values above what was expected. But the standard deviation for this particular sample size, this is that standard deviation calculation for this particular sample size, is the standard deviation of our sample, which is 15, over the square root of n, which is square root of 50. So we have 24 minus 20, 15 divided by the square root of 50 is 2.121. 2.121. And so 24 minus 20 is 4. 4 divided by 2.121 gives us what's called a t-score of 1.886. Okay, now to calculate our p-value, we are not going to use normal CDF. Okay, we are going to use what's actually called t-CDF. And the t is referring to the t-curve. Now the t-curve and the normal curve look very similar. But for this test, we use a t-curve. And the difference is that the t-curve is a little bit wider than the normal curve. So it has more values in the tail. So if I'm going to draw them out for you, just to give you a kind of a comparison. A normal curve would say looks like this. It's kind of taller and skinnier, whereas a t-curve kind of looks like this. It's kind of a little bit flatter and kind of looks like that. So like if you had a mean and you were 1, 2 standard deviations below, and you were 1, 2 standard deviations below, on a t-curve, this section is much bigger than it is on this one. Okay, and that's all. I'm not going to get into the why because it's too hard to explain on distance learning. So we're going to use what's called t-CDF. So you're going to get out your calculators and go to T-CDF, which is in the exact same spot you find normal CDF. So go to second VARS, and you're going to find T-CDF. It should probably be option 6, okay? And it's going to ask you for your lower boundary. So in this case, we're going from 1.886 to 999, all right, because we're doing a greater than test. There's the greater than test. So we're going from 1.886 to 999. And then it's asking you for something else, DF. And DF stands for something that we call degrees of freedom. All right? And that's what DF stands for, degrees of freedom. And I'm going to keep this as simple as I can for you. And degrees of freedom is a number, and it's the sample size minus 1. Because the T-curve actually changes depending on the sample size. So this degrees of freedom kind of defines what T-curve we're actually using. So in our situation, we have a sample size of 50, so the degrees of freedom value is going to be 49. So when you do T-CDF from 1.886 to 999 with 49 degrees of freedom, you get a p-value of 0.0326. All right? So the process mathematically is very similar to what you actually did yesterday. Yesterday you took your x bar, you subtracted what was expected, and then you had sigma over the square root of n as your denominator, but this time this is the sample standard deviation over the square root of n. Yesterday we called this a z-score. Now we're just calling it a t-score. Yesterday you used normal CDF. Today in the actual one sample t-test, we're using T-CDF. And actually the reason why all of this happens is because of this thing right here. The reason why this all changed is because yesterday this was the population standard deviation, and today this is the sample standard deviation. So that's why we have changed from a normal curve to a T-curve, because we changed from the population standard deviation to a sample standard deviation of 15. Okay? All right, so we identified a parameter, just like in a one proportion z-test. We identified our null and alternative hypothesis, just like in a one proportion z-test, but with mu instead. We checked randomization and independence. We named our test, a one sample t-test. We had a little bit the mathematics. This is where kind of you may have to come back and rewatch this, but this is how it works. And so our p-value is 0.0326. 0.0326. P-value 0.0326. 0.0326. So we should know that if the p-value is less than the alpha level, what do? We reject the null. So because the p-value equaling 0.0326 is less than an alpha level or significance level equaling 0.05, we reject the null, okay? And when you reject the null, that means you are accepting the alternative, and accept the alternative that, now, what is the alternative? That the mean reduction in cholesterol is greater than 20 milligrams per deciliter. That the mean reduction in cholesterol is greater than 20 milligrams per deciliter with the new drug. Okay? So the way you make your decision is exactly the same for both tests. If your p-value is less than your 5% alpha level, you are going to reject the null and accept the alternative and identify the alternative in context. If your p-value is greater than that 0.05, you're going to fail to reject the null, and then you identify the null in context. Okay, that doesn't change. Now, the last thing I want to tie into what we did last week, based upon your decision, what kind of error could your data have led you to? So in this case, anytime you reject the null, okay, when you reject the null, you're basically going to fall into one of two categories. Power is when your data led you to the correct decision. So if you correctly reject the null, that's called power. If your data led you to the wrong conclusion, that would be type 1 error. Okay? So all I want you to get out of last week is basically being able to identify what is power, what is type 1, and what is type 2. So if our data led us to a rejection of the null hypothesis, and that actually was wrong. So really the only being that knows this are the statistical gods. We don't know if we have committed type 1 error. But if our data led us down the wrong path, so if this conclusion is not correct, there is a possibility of type 1 error. All right, so here's what I would like you to do. The day 2 homework is this question. It's another test. I'm taking you through it step-by-step process. I would like you to submit the chapter 14 day 2 homework with the chapter 14 day 3 homework in one email. All right, so put it all together. If you're not ready to do a test yet, and you're like, man, I need to see another one, then watch the day 3 video before you try to do this homework. If you feel confident that you know what to do, go right ahead and do the day 2. But if you're like, man, I think I need to see another one to kind of get a better idea of all this, go ahead and watch the day 3 notes and then come back and do this homework with the other 2. But please submit day 2 and day 3 together. All right. Thanks, guys. All right. Enjoy your day. All right. And I'll see you, or you'll hear me on day 3.